Okay, so this lesson looks at net change as the integral of a rate. So we've focused on the area interpretation of the definite integral, where we've been using definite integrals to help us calculate the area bounded between two curves, or the area bounded between a curve and the x-axis. But now we're going to use the integral to compute net change. And you're probably like, well, what is net change? So let's look at this first situation. So water flows into an empty bucket at a rate of R of t liters per second. So R of t, we're saying, is basically a rate function where the inputs would be time in seconds, and then the outputs, R of t, would be the rates at any given time in which the water is flowing into the bucket. So we want to know how much water is in the bucket after 4 seconds. So the algebra 1 way of calculating this would be like, okay, well, let's say that water flows at a constant rate of 1.5 liters per second. So then the quantity of water in the bucket would just be the flow rate times how much time has passed. So in this case, it would be 1.5 liters per second times 4 seconds gives us 6 liters. However, that's not really realistic because things don't always change or at a constant rate. Like water doesn't necessarily flow into the bucket at a constant rate. So let's suppose that the flow rate, R of t, could be modeled by this graph that I'm sketching, where you could see that the rate would vary as time is passing. So the horizontal axis here represents t, time in seconds, and then the vertical axis represents R of t, so the rate at which, in liters per second, at which the water is flowing. And here, let's say this is our curve, R of t, where when the water first starts pouring into the bucket, it starts off kind of slow, and then the rate increases, and then it starts to slow down again, it looks like, as t approaches 4 seconds. So maybe like whatever you're pouring the water from is starting to become empty, or you're starting to pull back on whatever you're pouring from, so that or you're turning the water off or from a hose or something, the rate starts to slow down at t equals to 4 seconds, or as t approaches 4 seconds. Okay, so we're going to make this statement. The quantity of water is equal to the area under the graph. The quantity of water in the bucket after 4 seconds is actually going to be equal to the area under the graph of R of t. So this area here in liters would be the amount of water in the bucket after 4 seconds. And to prove this, we're going to have another function that we're calling S of t represent the amount of water in liters in the bucket at time t. Okay, so S of t is a function. We don't know the equation for S of t, but the input values would be times in seconds, and then S of t would represent the number of liters in the bucket at a certain time, whereas R of t represents the rate at which the water is flowing into the bucket at a specific time t in seconds. Okay, so the derivative of S of t would actually be the rate function. So the derivative of S of t would tell us the rate at which the water is flowing into the bucket. So S prime of t equals to R of t, because S prime is the rate at which the quantity of water is changing. So furthermore, S of 0 is equal to 0. That's because we are given that the bucket is initially empty. There's at t equals to 0 seconds, there are 0 liters of water in the bucket. So then by the fundamental theorem of calculus, if we were to integrate s prime of t, which is the same as integrating the function r of t from 0 to 4, this would be equal to s of 4 minus s of 0, which because there is 0 liters of water in the bucket, 0 seconds, that's just s of 4. So the number of liters of water in the bucket at t equals to 4 seconds. And since s prime of t is equal to r of t, and we know that evaluating the definite integral for a positive function over an interval will just give you the area under the curve. So it's the shaded area in here. Okay, so we are going to be able to calculate net change by taking the definite integral of, or calculating the definite integral of a rate function. So looking at this next example, so water leaks from a tank at a rate of 2 plus 5t liters per hour, where t is the number of hours after 7 a.m. and we want to know how much water is lost between 9 and 11 a.m. So we're given a rate function here. R of t is 2 plus 5t. And the graph of 2 plus 5t is a line with a positive slope. So that tells me that as time is passing, it seems like the water is leaking out of the tank at a faster rate. So we want to then integrate this rate function over an interval. So since t is the number of hours after 7 a.m., that means that at 7 a.m., t is equal to 0. So at 9 a.m., t would be equal to 2. And at 11 a.m., t would be equal to 4. So we're going to integrate r of t from 2 to 4. Oops, forgot my plus. Oh, we didn't. There's no t there. 2 plus 5t. Okay, so we can do this by hand. So we'll get 2t plus 5 halves t squared. And by the fundamental theorem of calculus, that will be 2 times 4 plus 5 halves times 4 squared minus 2 times 2 plus 5 halves times 2 squared. That gives us 34 liters. So we can say that 34 liters is lost from the tank between 9 a.m. and 11 a.m. Okay, our next example. So the number of cars per hour passing an observation point along a highway is called the traffic flow rate, Q of t, in cars per hour. So Q of t represents a rate function. We're going to interpret what the quantity, or what quantity is represented by the integral of Q of t from t sub 1 to t sub 2. So remember, when we integrate a rate function, you're calculating net change. So if Q of t represents the traffic flow rate in cars per hour, that means that the definite integral is actually going to represent the total number of cars that pass the observation point between t sub 1 and t sub 2. Okay, so over an interval of time, when we integrate the rate function there, over an interval of time, it'll tell us the total number of cars that have passed the observation point over that time interval. Okay, so in part B, the flow rate is recorded at 15-minute intervals between 7 and 9 a.m. We want to estimate the number of cars using the highway during this 2-hour period. So we don't have an equation for Q of T. What we do have is some data that's collected, so a table of values. Okay, so we are given... Okay, so what this table says, so at 7 a.m., the flow rate is 1,044 cars per hour. At 7:15, the flow rate is 1,297 cars per hour, and so on. So if we wanted to calculate, like if we had a function for Q of T, we would evaluate the definite integral from 7 to 9. Okay, but we don't have an equation for Q of T. We just have this table of values. So we're going to actually use our old friend, the Riemann sum, to help us estimate So we're going to use Riemann sum to help us estimate the number of cars that have been using the highway on that 2-hour time period. So looking at this table of values, we want to first calculate not delta x in this case, but delta t, because t is the independent variable. So we want to figure out what the length of each of the subintervals is going to be and how many subintervals we have. So we can see that from 7 to 7:15 a.m. is one subinterval, then 7:15 to 7:30, 7:30, 7:45, 7:45 to 8, 8 to 8:15, 8:15 to 8:30, 8:30 to 8:45, and 8:45 to 9. So it looks like the length of each of the subintervals, delta t, is 15 minutes, or because Q of t is in cars per hour, we can say delta t is like a quarter of an hour. If we want to actually do the calculation, the endpoints of the interval are 7 and 9, so we would do 9 minus 7, and then there's 1, 2, 3, 4, 5, 6, 7, 8 subintervals. Okay, so that would be 2/8, which is 1/4, or 0.25 hours. So remember, for Riemann sums, that was finding the sum of the areas of rectangles under a curve to help us estimate the area under the curve. So remember, we used either the left, the right, or the midpoints of the subintervals to help us find the heights of the rectangles. So here we're actually going to use the left endpoints of the subinterval, so the function values at the left endpoints, and then we're also going to use the right endpoints, and we're going to take the average of the two Riemann sums to help us estimate the number of cars that have passed the observation point between 7 and 9 a.m. Okay, so for using the left endpoints, I'll call that Riemann sum S sub L for left endpoints. So it'll be delta t, 0.25, and then times Q of t at all of the left endpoints of the subinterval. So 1,044, 1,297, and so on. Oh, I can fit it. Just move this over a little. Okay, so I get approximately 2,612 with using the left endpoints of the subintervals. Okay, and then right endpoints, again, delta t is 0.25. So I'll use Q of t, the value of Q of t at the right endpoints of the subinterval. So 1,297 plus 1,478. Okay, so I get approximately 2,487, and this is cars, right? Number of cars. So to estimate the value of the definite integral from 7 to 9 for Q of t, we're going to take the average of these two Riemann sums. So add them together, divide by 2, and we get approximately 2,550 cars. So we can say that approximately 2,550 cars passed the observation point from 7 a.m. to 9 a.m. Or we could say approximately, I guess the question said estimate the number of cars using the highway during this 2-hour period. So approximately 2,550 cars were using the highway between 7 and 9 a.m. That's another way you can summarize your answer. Okay, so the last part of this lesson is talking about the integral of velocity. So remember, velocity has both magnitude and direction, where the magnitude of velocity is the speed at which an object is moving, and then velocity also should have direction. So if we let s of t be the position at time t of an object in linear motion, then the object's velocity is v of t, which is the derivative of the position function. So s prime of t equals 2v of t. And the integral of v of t is equal to the net change in position, which is actually the displacement of an object over a time interval. And we need to talk about the difference between displacement and distance traveled, because and you've probably talked about the difference between displacement and distance traveled in your physics class. But if you travel 10 kilometers and then walk 10 kilometers back to your starting point, your displacement is 0, because displacement is the distance from where an object starts and where it stops, or where the object is at the end of an interval of time. However, your distance traveled would be 20 kilometers, because you've walked a total of 20 kilometers. So to compute distance traveled rather than displacement, you would just integrate the magnitude of velocity, which is speed, the absolute value of the velocity function. So when we take the integral of velocity, if you're calculating displacement, you're just integrating velocity over an interval of time. And if you want to calculate distance traveled, you need to integrate the absolute value of the velocity function, which is speed. Okay, so here we're given that a particle has a velocity v of t equals t cubed minus 10t squared plus 24t meters per second. So basically this function, if you plug in time in seconds, it'll tell you the velocity of the particle at at that moment in time. So to calculate displacement over, it looks like the first 6 seconds, from 0 to 6 seconds, we can actually just integrate from 0 to 6 this velocity function. Okay, so when we do that, we'll get 1/4 t to the 4th minus 10/3 t cubed plus 12t squared. Okay. Okay, so then if we substitute in 6, so by the fundamental theorem of calculus, we'll substitute 6 in. And when I substitute 0 in, I would just get 0. Okay, so this is 36 meters. So the displacement of the particle is 36 meters, meaning the distance from where the particle was at 0 seconds to the location of the particle at 6 seconds is 36 meters. And then part B, we want to calculate total distance traveled. So that's going to be the integral from 0 to 6 of the absolute value of t cubed minus 10t squared plus 24t. So if we wanted to do this by hand, we would need to think about the graph of v of t from 0 to 6 seconds. And if the graph dips below the x-axis over that interval at all, then we'll need to split up the integral in order to calculate basically the area between the curve and the x-axis. Or you can use your TI-84. So if you use your TI-84, okay, you're going to hit math, and then number 9, right, is let me see what it is. So number 9 says fn int, but that's how you pull up the definite integral. You guys have done that. So then you'll put in your lower limit as 0, your upper limit as 6, and then to type in the absolute value, you hit math again. So then you type, put in your limits of integration. Oops, can't spell. So type in your limits of integration. Okay, lower limit 6, or 0, upper limit 6. Sorry, lower limit is 0, upper limit is 6. Okay, so then to type in the absolute value, you're going to hit math, and then you're going to arrow over to the right to the num menu, and number 1 is going to be abs. So that'll pull up the absolute value bars, and then you can type in the function. But remember, it's going, your independent variable is going to be x. So you're going to actually end up typing in x's and then dx, okay? And then you can hit enter, and you will end up with approximately 49.3 49.33333 so on, which is actually 148 thirds. So the total distance traveled, and that's exact actually. So the total distance traveled for the particle from 0 to 6 seconds is actually approximately 49 meters. whereas the displacement was only 36 meters. So the particle has actually traveled further than what its displacement is. And that's because it's probably gone in the positive direction and then a little bit in the negative direction and back in the positive direction. So that's where we get the total distance traveled being greater than displacement. Okay, so I have some practice problems on here, and I will send you my worked out solutions to these practice problems.